Okay, I took a pause for a second because I didn't like the way that the board was looking. I was getting confused again. So I came up with something simple, and I think it should be now crystal clear. So consider something here looking on the left where we have these 4 coordinates. Now there is an input at 1, there is an input, well, let me just not say 1. There is an input here and an input here, and there is an output here, here, and here. I'm going to call them with letters A, B, C, D. Now, when we do the system identification, we will have the vector phi in any given mode at A, B, C. So look at it here, A, B, C. That's the vector phi, right? We will have this vector here, the other type, C, let me call it. I don't remember the name. We would have that one where? At A and D. A and D. Therefore, we would have a matrix 3 by 2 in which we would know these 6 numbers. Now, if we figure that we're going to expand it to the phi, then this is phi transpose times gamma. So this is phi's at A, B, and C, phi at A, B, and C, and gamma. If we multiply all these things and we compare with this one, we can see that this term, which is the AA term, here, we know it. So we can say this term must equal this term. This one, which is the AB term, we know it here. So we can compare it to this term. And this one here, the CA term, we know it, so we can compare it to this term. Now, this column is the phi with the B. We don't have a B here, we only have a D. This is the C. We don't have a C here. So of this matrix, only this column matches this one. Therefore, I can say, since these 2 numbers must be the same, we can write this equation that says phi A times CA, this term, must be the same as phi A times phi A again times the constant. Or if I choose this one, phi B times CA, this one, phi B times CA, must equal phi B times phi A times the constant. Either way, when I substitute, I get, for both cases, this expression, which says the constant for this mode is CA divided by phi A, or CB divided by phi B, or you could get the same thing in C. You would get CC divided by phi C, right? All those numbers would be exactly the same, okay? All those numbers would be exactly the same. Now, if they were not exactly the same, by the way, just to give you the first hint, if they were not exactly the same, which one would you be? I mean, you could think in terms of averaging or getting something, but no. Normally, what we would assume is that the value of the vector that is largest in absolute sum has the least error. So if this phi A was 0.0001 and this one was 3, I would certainly use this second term to get it, because the denominator is large and I feel more confident with it, okay? That's what I meant. In case there was more than one collocation, you could actually, if there was another column that was collocated, you could have used the other, and so on, okay? So this gives you the constant gamma for that mode. On the next mode is the same picture. On the next mode is the same picture. On the next mode, and so on. So having said that, I'm going to just to make sure nothing was left unclear. What happened? Okay, so I am going to write here the 3 lines that I used in the function that I wrote. So my MATLAB function is called db expand. And in this function, I bring in Now you can do it with discrete or with continuous. Actually, with continuous would probably be faster, but the way I wrote it was I assumed I just had my discrete time matrices at the time, so I put my discrete time matrices. Now this is collocated input and this is collocated output, and delta t. I'll talk a little bit later on something else. And on this side I have what I'm going to eventually pull out is my B expanded and my C expanded, and I'll add a little bit later. But in any case, let me just say here, without giving the specifics, that I get A continuous and I get B continuous using the formulas that we know, right? Then we calculate let me use the same notation I'm using in the code here. So I'm calling it F and lambda to be the eigenvalues of A continuous. Okay, then tau, you give it any letter you want, is the inverse of F multiplied times B continuous with the formula that we've written a few times. And phi, which I called phi like this, is equal to C continuous times F. Okay? Then I say compute gamma. And it's 3 lines. It says for j equals 1 to the order n, calculate gamma j equals to tau j collocated input divided by phi collocated output j. N. So what I have talked about in theory is just these lines. Okay, let's see if it's being taped. Yes. Okay, so that is all that I have done. Now, what is collocated input and collocated output? Those are the numbers. So once again, if this is the system that we have, and I have an input, let's say in this order, and then output 1, output 2, output 3, output 4, then if which one is collocated? Well, I have input 1 is not collocated, input 2 is collocated, right? So I can say here that the collocated input is the second one, because I'm putting it in this order, and the output in which it is collocated is also the second one. So it would look like that in the code, right? If instead there was no output here, and the first output was here, then we would say the second input, collocated input is the second one, is collocated with the first output. Okay? Like that. So that's the way that this code works out. Now, the rest of the code actually is written, which is what I asked you on the homework, and I want to give you a day or two to try it yourself before I give it to you in case you have a difficulty. And the point is, it should be, I think you get it, that you can use the same logic. Once you've got these constants, you can use the same logic to actually solve for the union of the coordinates. So that with what we've done right now, if all you have is one collocated input, you know, input, output, 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 then that's it. There's nothing else to do. But I generalize my code so that if I also have another input here and another input here, so input 2, input 3, and they're not collocated, I can also expand to those. Okay? That's what I'm asking you to give it a shot. You know, give it whatever, give it an honest effort. The code is already ready. I've already tested it. Everything is going to be fine. So, you know, do what you can and let's get it done by this coming week. With regards to, so I guess this is, oh no, there's one last word. One last word. Remember that tau is equal to phi to the minus 1 times b, right? Times b continuous. After expansion, you can say that you'll have that phi to the minus 1 times bc will be equal to your phi's expanded times the alphas, because now this is what we have, right? Transpose. Now, yeah, this comes from the fact that we wrote the equation like this, right? So this part here is the tau, right? So the tau, which is phi to the minus 1 bc, is just this, okay? So you can then say that your b expanded is simply equal to phi multiplied times your phi expanded times alpha transpose. So this is the final formula that gives me my b expanded. Likewise, we have that the c continuous times times the matrix phi. Now why do I do that? Yeah, is going to be my phi expanded, right? If I get any more coordinates, it's going to be like this. Therefore, my c expanded is going to simply be equal to my phi expanded times phi to the minus 1. So if I want to present my results in terms of the enlarged matrix B and C, then that's all I have to do once I expand my mode shapes. They look this way. Okay, so now that you copied that, let me finish with the question on the B. Why didn't I mention the B? Why no D? Because we can calculate D after the fact, as follows. Imagine that you have x dot is equal to ax. I think Andrew asked a question like this at the beginning of the course, and I said, yeah, the Markov parameter and so on. So it'll probably come to your mind again. This is like this, right? Now imagine that what we have here is displacements. So I'm going to call it C displacements times xt, right? Now, if you take a derivative of y, that will be c displacements times the derivative of x. But the derivative of x is axt plus bft, right? So that would be that y dot is equal to c displacement times a times xt plus c displacements times b times ft, right? If you take another, well, anyway, in this case, this is a plot of accelerations, I mean of velocity, right? And we know that for velocities there is no d, so that tells us that that product must be 0. If we take another derivative, two derivatives of y would be c displacements multiply times a multiply times x dot, which is axt plus b BFT, right? Therefore, we have that y double dot, if we were measuring accelerations, would be c displacement a squared xt plus c displacements a b ft, right? But we recognize that if we were measuring accelerations, this would just simply be the c acceleration, right, times xt, and this would be d times ft, right? Therefore, what do we conclude from that? What do we conclude? We conclude that d has an expression which is c displacement times a times b, right? Cool? But what else do you gather? You gather from here that c acceleration, which is this, is c displacement times s times a squared, right? C acceleration is c displacement times a squared, correct? So, if what you had done was to do, well, forget that. That just means that from here I can say that c acceleration times a to the minus 2 is equal to c displacement, right? Therefore, plugging in here, instead of c displacement, I can put c acceleration times a to the minus 2, which times a is a to the minus 1 times b, right? And now I have an equation for d in terms of the measurements that are accelerations and in terms of the a and the b. Therefore, in continuous time, therefore, if I am doing an ID, there are some issues here of truncating modes and so on, but theory is this. So if I am measuring accelerations, okay, the c that I get is CA because I'm measuring accelerations. I'll get an A and I'll get a B. And once I have that, that's the D, right? That's the D. So in my computer code, actually, I wrote B expanded, C expanded, and I also called it D expanded. And then inside the code, I put that if the accelerator, here I put dB expand, and in addition to the inputs, I put a flag. If this is 1, I am measuring accelerations. And so the program outputs D. If this is not 1, then the program outputs just a 0 as a warning, because there is no D. Okay? And when it's measuring accelerations, it interprets the input C as being CA, and it calculates the D like this. After the C is expanded and the B is expanded. So on Monday, I will run the code briefly. Well, not briefly, I mean, I'll run it to whatever your satisfaction is. Hopefully you can get something done from now to Monday. And then we move on to a stochastic identification. Please note that the notes are, the stuff on stochastic identification is in the posted lectures, and also there is the theory on this stuff is also there. So in case I left something unclear, maybe you can get additional clarification from the notes. And so hopefully Monday we will take care of a stochastic ID, and maybe by the beginning of next week, or not the week coming, but I mean, the week after that, we can have enough material to start thinking about papers. Okay? All right, that'll be